Hi everyone. In this video, we'll continue our discussion of trig functions and their inverses. First of all, what actually is an inverse trig function? We've all used the sine inverse and cos inverse buttons on our calculators, but on the other hand, we know that trig functions don't pass the horizontal line test, meaning, strictly speaking, they don't have inverses. So what do we really mean when we talk about inverse sine, and what does that button on your calculator actually represent? Well, we can have an inverse function provided that we restrict the domain. If we only allow for x values, which are between minus pi over 2 and pi over 2, then the curve we have here does pass the horizontal line test, and so with that restriction, we can define the inverse sine function. I've made this caution before, but I'll remind you once again that the inverse function is not the same as a reciprocal. The notation we use for inverse sine looks like a power of -1, but it actually is not a power of -1. So be cautious that these two expressions that look very similar actually have very different meanings. To avoid that type of confusion entirely, it's common to also refer to the inverse sine function as arcsine. Personally, I prefer to call it arcsine and will do so the majority of the time from this point forward, but you can use whichever of these notations you prefer as long as you do so correctly. So far we've only talked about inverse sine. So which domain restriction would be required for inverse tan? The restriction we use should allow for as large a domain as possible while still ensuring the curve passes the horizontal line test. So for that reason, we use the interval from minus pi over 2 to pi over 2 for this one as well. And with this restriction, we can define the inverse tan function, otherwise known as arctan. What about the secant function? You can see here that the graph of secant x also doesn't pass the horizontal line test. So we restrict the domain just to this interval from 0 to pi, and with that, we can define inverse secant, otherwise known as arcsecant. So far, we've got arcsine, arctan, and arcsecant, and it turns out those three are the only ones we need for building useful integral formulas. So, you could, of course, also consider arccosine, for example, but it's not important to do that for our purposes, so I'll omit that from our discussion here. Now that we've defined inverse trig functions, let's make sure we understand how to do calculations with them properly without having to depend on a calculator. Mainly so that you have a good understanding of how these functions actually work, rather than just thinking of them as the magic button. When it comes to trig functions, normally what you want to think of is that you have some angle, and when you apply a trig function to that angle, you get some ratio, such as opposite over hypotenuse or opposite over adjacent. The particular ratio you get just depends on which trig function was applied, whether that was sine, cosine, tan, or whatever. Now, what the inverse trig function wants to do is return us back to the angle that produced that ratio. However, I shouldn't say the angle, because there's always more than one possibility, either by looking in a different quadrant or by adding 2 pi. So the inverse trig function has to decide which of the many possible angles to return, and that choice is always made by using the domain restrictions I mentioned earlier. So just to recap, arcsine is only capable of returning angles between minus pi over 2 and pi over 2, and similar restrictions were applied when defining arctan and arcsecant. For the future, I'm expecting you to know these restrictions so that you can use them to do calculations with these functions, so you should either memorize them or make sure to have them on a formula sheet. It can also be useful to think of these restrictions in terms of quadrants, which might be easier for you to remember. Let's try an example. Find the value of arcsine of 1 over root 2. When it comes to these types of problems, I like to start by clearly identifying whether what I'm looking for is a ratio or an angle. But we know that inverse trig functions always return angles, so that's the type of answer we should be looking for here. Let's start by giving a more convenient name to this angle we're looking for. I'm going to call it theta. Now, what do we actually know about this theta? Well, we know that it corresponds to a sine ratio of 1 over root 2, which you might visualize using a diagram like this. In other words, theta is an angle that has a sine value of 1 over root 2. So which angle would that be? Well, you can use the unit circle to figure that out. I assume you know how to use the unit circle, so check for yourself that pi over 4 and 3 pi over 4 are both possibilities. So one of these is the value of arcsine of 1 over root 2, but which one is it? To make that decision, we make use of the domain restriction. Since arcsine can only return angles which are between minus pi over 2 and pi over 2, we must reject the possibility that theta is 3 pi over 4. On the other hand, pi over 4 does fall within that stated interval, so we can declare that as our final answer. Here's another example. The answer to this question is actually less obvious than it appears, so let's be careful not to make assumptions and let's work through the details very carefully. First, ask yourself whether what we're looking for is an angle or a ratio, just like the previous example. Since we've been asked to evaluate an inverse trig function, what we're looking for here should be an angle. So let's call that angle theta, just like before. And what do we know about this theta? Well, we know it corresponds to a certain tan ratio, but which tan ratio? Well, that would be represented by this entire input. In other words, we know tan of theta must be equal to tan of 7 pi over 6. Now we can use the unit circle to determine which theta values match these criteria. For starters, it's pretty clear that theta could just be 7 pi over 6. But there are other angles that could produce the same ratio, so we should make sure to consider all the possibilities. 7 pi over 6 really represents the quadrant 3 possibility as you see here, but according to the cast rule, there should be another angle in quadrant 1 which produces the same tan ratio. And that shows that pi over 6 is actually another option. We could also add or subtract 2 pi to get even more options from here. So out of all these options, which one is the value that we're looking for? To make that decision, we look at the domain restriction which defines inverse tan. We must be looking for an angle which is between minus pi over 2 and pi over 2. And the only possibility that matches that condition is pi over 6. So in conclusion, this is the value we're looking for. If you're surprised by this answer, it's possible that you fell prey to a common misconception about inverse trig functions. So let's talk about misconceptions. When we see inverse functions applied in succession like this, tan followed by inverse tan, it's common to think of these inverse functions as canceling each other out, returning the x value that was inside. But by that logic, the previous example should have provided us with an answer of 7 pi over 6, and that's not the answer we found because tan inverse isn't capable of providing that answer. So that means there's something technically wrong with canceling these things in such a way. So in fact, the statement written there is technically false, but when we think about why it's false, it's because, as I just said, tan inverse is only capable of returning angles which are between minus pi over 2 and pi over 2. So as long as x represents a value which is in that interval, then tan inverse is capable of providing that x value as an answer, which would make for a valid cancellation of the inverse functions in that case. A similar comment applies to inverse sine and inverse secant. We can cancel the inverse functions like this only when the input belongs to the appropriate domain. This also raises the question of whether we could cancel when we apply our inverse functions in the opposite order, such as sine of sine inverse rather than sine inverse of sine. In this scenario, would we be able to cancel these inverse functions to get a result of x? The answer is yes, as long as the expression I'm dealing with here is actually defined. On the other hand, if it wasn't defined, it's likely not an expression you'd be considering in the first place, so that's not really a condition you need to worry about in practice. So in short, you can always cancel when taking sine of sine inverse, but if you're taking sine inverse of sine, you'd need to be careful about the domain restrictions. The same can be said about these other functions as well. Let's try one more example. As a first step, let's ask whether what we're looking for here is an angle or a ratio. Pause and think about it. I hope you were able to answer that what we're looking for here is a ratio. That's because the arcsine of -3/4 here is going to provide me with an angle that you might call theta, but then you're taking the secant of that angle, which will provide us with a ratio at the end of the day. So let's start by defining the angle theta as arcsine of -3/4, similar to what we did in other examples. And what do we know about this angle? Well, we know it has a sine value of -3/4, and we know it must be between -π/2 and π/2 according to the domain restrictions of arcsine. But the goal of this question isn't to find theta, it's to find secant of theta. Since secant is the reciprocal of cosine, we know this would be calculated as hypotenuse over adjacent. But to calculate that ratio, we need an actual triangle to work with, so let's sketch our angle with the information that we've been given. But which quadrant should I sketch my angle in? Well, for starters, our domain restriction tells us that our angle must be either in quadrant 1 or 4, so we know these other two quadrants aren't possible. To narrow things down even further, we can use the cast rule. In this case, we know that the sine of our angle is a negative value, so we can't be working in quadrant 1. And by the process of elimination, we're safe to sketch our angle in the only remaining quadrant. Now, in order to calculate hypotenuse over adjacent, we need to know the dimensions of this triangle, but we can figure that out using the sine ratio that was given to us. In particular, we know this ratio can be viewed as opposite over hypotenuse, and so we can label those sides in our diagram. Technically speaking, though, the opposite side should be labeled as -3, since the y values in this quadrant are all negative after all. With this, we know the hypotenuse is 4, but what about the adjacent side? For that, you can look back to the diagram and apply the Pythagorean theorem to find that side has a length of √7, and that's all we need for calculating the secant of theta, and that completes the problem. I found that students tend to have a lot of trouble answering questions like this, so my advice is to always start by identifying whether you're looking for a ratio or an angle, and draw a good sketch to help yourself visualize the information you've been given. That's all for the basics of inverse trig functions, so I'll wrap things up here and see you next time.